Mhm.
Okay, this should be working now. So please go ahead. Remember, you have like 45 minutes, and then we will have questions.
Oh, of course. No, not a problem. So here I am here to present a seminar on fermionic dark matter and its self-interactions, present a few novel approaches to these sort of models, and introduce a few future probes that can give us a hint about the nature of these models. Most of the work I will present now has been the subject of my PhD thesis. It was directed, advised by Professor Carlos Argüelles, and with a few collaborators in Professors Lopez Nasir, Skokola, among a few others. So, most of our research into fermionic dark matter models has been motivated by recent tensions to Lambda CDM predictions. Some of these tensions to the standard model of cosmology has been, for example, missing satellites, that the number of predicted Milky Way satellites from dark matter only simulations is sometimes thought to be inconsistent with observation of the galaxies of the Milky Way. It is thought that the number of Milky Way satellites observed is much smaller than the predicted number. The too big to fail problem that the most massive subhalos predicted in these dark matter only simulations should be luminous and are indeed not observed, and the core cost problem that the inner dynamics of dark matter halos, mostly in the case of small dark matter halos, is sometimes consistent with the dynamics of small dwarf spheroidal galaxies, among other dimensions. Now, what these problems have in common is that they involve short scales, small scale structures, typically of subhalo size or lower. So to first tackle this problem, we can take a look at the process of formation of these structures in or their host halos. So the process of halo formation is given by this system. This is the Vlasov-Poisson system. It describes a collisionless fluid evolving through the effect of self-gravity. Typically, this equation is resolved in the context of structure formation by n-body simulation. One puts a very large number of order solar mass particles to evolve in an expanding box in order to gain insight into clustering, formations, history, etc. Here we will focus on a slightly different approach to this system. We will focus on analysis of this equation. This equation shows no steady state solution and instead develops a complex filamentation process in phase space. The phase space stretches into large thin filaments and obviously has no steady state solution. But if we split this distribution function into a coarse grain component, this coarse grain component is averaged over these filaments and a perturbation, we can see that a steady state solution is indeed possible for this coarse grain component. This was realized early in a work by Lind and Bell, and it was seen that this steady state solution resembled a Fermi-Dirac distribution. These early results were generalized much later in a series of papers by Chavani via a maximum entropy production principle, assuming that this system produces the maximum amount of entropy possible at any given time. And with this, one ends up with an evolution equation for the coarse grain distribution that resembles a Fokker-Planck diffusion equation by the effect of these perturbations. So here we will focus on the steady state solution of this system at the coarse grain level. We can see here, for example, the Fermi-Dirac distribution function with the added effect of tidal truncation. This reflects the process of incomplete relaxation towards the outer edges of the halo. This distribution is important because it has a straightforward astrophysical application. We can use this distribution to construct dark matter halos. How we go about doing that is we start from the TOV equations, the Tolman-Oppenheimer-Volkov equations that describe a general relativistic fluid in spherical symmetry. And instead of using the standard equation of state for the energy density and the pressure, we use a non-parametric equation of state constructed via this distribution function. To this system, we add astrophysically relevant counter conditions in order to describe a halo, for example, its total mass, concentration, total radius, or other combination of observables. And we end up with a relevant model that can describe the dark matter halo. A subset of these solutions is the extended RAR model, RAR for Ruffini, Argüelles, Poeda. Here we can see the solutions that correspond to Milky Way-like counter conditions. It is important to remark that there also exist solutions for dwarf galaxies, for elliptical galaxies, among other types. Here, right here, we can see the density profile for these solutions. We can see that this has a distinct core halo structure with a very dense inner core and a more extended halo over here. This core is this core is actually supported by the phenomenon of quantum pressure, and in this core the relativistic corrections become somewhat relevant. Here in this other plot we can see the rotation curve for these models, and on top of them the observables for the Milky Way rotation curve. You can see that all of these observables constrain the particle mass to be in the range between 48 and 345 keV. Indeed, this range of masses can make these profiles consistent with all Milky Way observables, including the stars in the S cluster, the stars that orbit the closest to the center of the Milky Way. This results in this profile having the inner core of this profile being a considerable alternative to a central supermassive black hole. We can see this in detail with this comparison of the orbits of the S2 star, the star that orbits the closest to the center of the galaxy, between the orbit given by a supermassive black hole and this central core. We can see here that the orbits for this star are almost identical. We conclude by this that this inner core can actually be a compelling alternative to a central black hole, at least in our galaxy. We also performed the full thermodynamical analysis of these solutions in a recent paper right here. I will not provide a lot of detail into this, as this was the main subject of a previous seminar by Professor Argüelles here in this institute a while ago. I will simply measure that the preferred parameters for the Milky Way data are located in a region of thermodynamical stability, as can be seen here by this caloric curve done in the microcanonical ensemble. We also found a region of actually unstable core halo solutions, and here we argued that this region could allow for a mechanism of early supermassive black hole formation just via dark matter core collapse, without requiring mechanisms that would require super Eddington accretion rates in the early universe. So now we have seen that the fits for the Milky Way data of these RAR solutions would constrain the particle mass to be of order 10 to 100 keV. This is certainly not the preferred mass range for cold dark matter, CDM, the standard dark matter model, and instead puts us in the range of more warm dark matter models. These are characterized by slightly lighter particles than CDM, which are produced while they are relativistic, but become non-relativistic before the matter-dominated era of the universe happens, unlike models like hot dark matter. These models have the characteristic of having large initial velocity dispersions. This in turn free streams out of dense regions, inner dense regions, and erases structure at small scales. This has the effect of relaxing some of the small scale tensions, particularly missing satellites and too big to fail. We can see this a bit more clearly in this plot right here. This is the warm dark matter power spectrum suppression. This is the power spectrum that measures the roughly the amount of structure at a given weight number in the universe. We can see in black the predictions for cold dark matter models, and here in colored lines various warm dark matter models. We can see already a significant suppression happening at 10 inverse megaparsecs and higher. We can quantify these suppressions by the free streaming scale lambda here. For typical warm dark matter masses consistent with these rare models, this streaming scale would be of 10 to the 5 solar masses and lower. A structure smaller than 10 to the 5 solar masses would be significantly population suppressed. So in our research, we focused on a particular particle physics model, the neutrino minimal standard model, or NU-MSM. In this model, warm dark matter is comprised of stereo-neutrinos that are produced out of equilibrium and require only a rather minimal extension to the standard model of particles, only a Majorana mass term for the right-handed neutrinos. However, our conclusions are not really limited to this model, and indeed they can be either directly applied or minimally extended to other warm dark matter models as well, or even a more general class of self-interacting models. We have focused on this one because it is well studied in the context of particle physics and cosmology, and consequently it is rather well constrained. This constraint comes in the form of X-ray observations due to predicted stereo-neutrino decay, Big Bang nucleosynthesis puts bounds on production mechanisms of these particles, and particularly Lyman alpha are one of the most constraining observations for these kinds of models. We can see the constraints here in a plot of the parameter space for this model, the particle mass versus theta, the interaction angle between the dark and the standard model sectors. Here we don't plot the Lyman alpha bounds because they would exclude actually most of the available parameter space for this model. Indeed, also excluding the preferred mass range for rara halos given by Milky Way observables. So for us, that motivated a small extension to this non-MSM model in order to first alleviate these tensions in stereo-neutrino warm dark matter, and also reconcile these two models that we were having in mind. So based on well-studied extensions to cold dark matter model, we proposed the phenomenon of self-interactions between dark matter particles. These are simply elastic, purely elastic collisions between dark matter, and we can measure this by an effective cross-section sigma. So we added the effect of self-interactions to warm dark matter models based on NU-MSM, and we labeled this as self-interacting warm dark matter models. So we started by taking a look at direct constraints from the morphology of the M halos in this new particle physics context in this paper right here. We found a number of interesting conclusions that these profiles are not significantly affected by the presence of self-interactions if we limit ourselves to the interaction cross-section allowed by observations of the bullet cluster. We also considered how these X-ray constraints are modified when we consider the radar system for the Milky Way halo. We found rather similar bounds, but with important changes to the preferred observation targets. We saw obviously that this central inner core becomes a prime observation target for the decay of stereo-neutrinos, and actually it can provide actually more stringent bounds at other regions of the halo. We also found and discussed new or enhanced by self-interactions production mechanisms in this paper right here. We could also ask ourselves whether the collision or relaxation mechanisms that drive the formation of these rare halos in the first place is affected by these self-interactions. If we looked at the evolution equation for the post-grain distribution function, we can see that the effects of the perturbed, the fine-grained evolution on this system resembles a Fokker-Planck collision term, as I mentioned before. Now, obviously, the effect of actual collisions could potentially add another relaxation mechanisms that contribute to the relaxation to the steady state. It could potentially alter initial conditions for the formation of these profiles. However, these still remain as open questions and the subject of future research. Now, so far we discussed about the potential effects of the combined model of Rafael's with NUMSM and hinted at the prospect of self-interactions. Obviously, this motivates a direct follow-up regarding the cosmological effects of Warner matter models and how are these altered in the presence of self-interactions. So we studied the effects of self-interacting Warner matter in cosmology. These can have potentially relevant effects in many stages of the universe, for example, production in the early universe, as we mentioned before. And also, we will focus on the rest of this seminar in the background and perturbation evolution in the presence of self-interacting Warner matter and how this has effects in observables for structure formation. Now, to deal with the effects of self-interactions in Warner matter, we start by the treatment of standard Warner matter with the expression for the perturbed Friedmann-Robertson-Walker metric right here. We can express the evolution for this perturbed part of the metric via the Einstein equations. Here we can see the Einstein equations for the evolution of scalar perturbations. Here we can see that these are sourced by perturbations in the energy momentum tensor of the universe. For different species of the universe, the evolution of this energy momentum tensor looks differently, but for the case of Warner matter, one needs to invoke the Boltzmann equation to obtain the evolution of these perturbations. Here we can see it expressed in general relativistic terms. If we wanted to add self-interactions into these systems, one needs to add a term that accounts for the collisions in these species. This looks as a right term in the right-handed side of the Boltzmann equation. Now, how are these collision terms written? Well, here is the expression for the full Boltzmann collision term in the case of elastic collisions and neglecting the effects of quantum population in these particles. We can see here that this is a rather complicated 9-dimensional integral that involves the Feynman amplitudes right here and is to the power of 2 in the distribution function itself. This the function that we are solving for in the Boltzmann equation. So it is important to reduce this integral expression in order to do some calculations, either analytical or numerical. We did this in this work here in terms of an ansatz for the interaction amplitude. We assumed a second-order polynomial for the interaction amplitude in Mandelstam variables. This ansatz is exact for many massive mediator models, along with some other relevant examples. This reduced form, we consider this based on kernels. Here we can see the expression for the first-order collision term, and it's based on these kernels chi and k. This expression is exact once we assume the ansatz, and it makes no assumptions in mass, either heavy mass for the dark matter particles or light. This is ideal for its application in warm dark matter models. And all of the information on the interaction model is encoded on the kernel itself. The ansatz we assume is exact for example, massive scalar interactions in the tree-level approach, obviously. Also for vector field interactions, for fermion interactions, among others. So this collision term can be approximated further via replacing this operator by a simple one. We can take advantage of the fact that collisions in this distribution function drive it to an equilibrium form. If we assume this, we can propose a simpler operator like this that simply would drive any distribution function to its equilibrium value in a characteristical time tau. This would be, in this case, the time scale of these interactions. This time scale tau is known as the relaxation time, and the whole approximation as the relaxation time approximation in the literature. So we can estimate this quantity, or rather the inverse of this quantity, in terms of the pre-computable kernels we expressed before, via this expression right here. So we can use this new operator to solve the Boltzmann equation, or to give an expression for the Boltzmann equation. Here we can see the Boltzmann equation for first order perturbations to an isotropic background. Typically, for this equation, what one does in order to solve it numerically is to expand it in Legendre polynomials in the angle between the wave number and the comoving momentum. Once one does that, one reaches an infinite hierarchy of equations known as a Boltzmann hierarchy. This is the exact same system of equations that one would solve in order to calculate the consequences of warm dark matter in a cosmological setting, with the only addition of these collision terms right here in the relaxation time approximation. We canceled out the first two collision terms in order to restore number density and energy density conservation in what is sometimes known in the literature as the Lorentz model. So now, as we already considered the first order approximation, let us focus now on the background. For that, we need to study the zero order Boltzmann equation that is expressed right here. This equation is rather simple, and it simply states that the comoving evolution of the background is simply given by the effect of collisions. Now, instead of dealing with the full equation, we will focus on a few emergent effects regarding thermodynamical equilibrium. When self-interactions dominate on the system, which happens when their interaction rate overtakes the expansion rate of the universe, measured by the Hubble constant h, the distribution function remains in kinetic equilibrium as self-interactions maintain this equilibrium. Now, once this rate falls under the Hubble rate, once this rate is overtaken by the expansion rate of the universe, this kinetic equilibrium maintained by self-interactions is lost, and the distribution function is now frozen on its last value and simply evolves through redshift of its momentum. This moment is known as the decoupling, or in this case, as it is maintained by self-interactions, the self-interaction decoupling of these species. If this moment of decoupling happens while the species is still relativistic, then the evolution of the distribution function remains similar to what would happen in standard warm dark matter. But if this happens when the species is already non-relativistic, we have an interesting new situation that we name non-relativistic self-decoupling. Sometimes in the literature, this is known as late kinetic decoupling. It simply implies that the distribution function is maintained in equilibrium through the non-relativistic transition. So the equilibrium itself transitions from a relativistic form to a classical or non-relativistic form, and the distribution function itself follows as it is maintained in equilibrium through this transition. This decoupling is rather similar to another forms of decoupling through the early universe evolution of this species, but it is slightly different in the sense that it is only kinetic equilibrium as it is maintained via elastic collisions. This entails that there are a few conserved quantities through the transition from relativistic to classical, for example, the number density, the energy density, the pressure, among others. So we calculated in this paper right here the consequences of this scenario in linear cosmology. We calculated the distribution function, the non-relativistic distribution function today. We performed a few transition approximations for the background and the perturbations. And we expressed a few reduced forms for the interaction rate gamma in these scenarios. So with this in place, we developed a numerical application for these self-interacting warm dark matter theories. We implemented these models in class, a public Boltzmann solver with a rather robust code base for warm dark matter. And we modified this code to account for self-interactions. We pre-calculated the relaxation time. We added the effect of dark matter tight coupling when this relaxation time is small enough. We implemented this scenario we mentioned about non-relativistic self-decoupling, which entailed integration updates, approximations for the switching of the background distribution, etc. And here I would like to mention that we are maintaining a public repository with this code. So if you want later, I can leave it in the chat, and so you can check it out. So as we are interested in the consequences of these models for the process of structure formation, we will take a look at the power spectra for these models. Here we can see them in this plot right here. In black, we can see the predictions for cold dark matter models, and in solid blue and red lines, we can see reference warm dark matter models corresponding to non-resonant reproduced neutrinos of 1 and 10 keV respectively. So over this, we added self-interacting models with increasingly higher interaction strengths. And here in the lower panels, you can see the transfer function of these interacting models with respect to the warm dark matter counterparts. We can see that these interacting models are similar to warm dark matter for the same mass, particularly the low interaction models. But as the interaction grows higher, the interaction constant grows higher, and the species becomes in the non-relativistic self-decoupling regime, we can see some interesting behavior. The profiles become colder, i.e. as it corresponds to a higher mass particle, and we can see a distinctive pattern of oscillations for interaction constants high enough. I would also like to remark here that we also calculated the consequences for CMB observables for CMB modes, but we found no difference from the interaction models with the non-interacting model. So we can compare these linear theory observables. We can use these power spectra to compare these with linear theory observables. In particular, we will take a look at the predicted number of Milky Way satellite halos, which can be obtained under linear theory using the Press-Schechter formalism, with this expression right here, potentially relating to the mixing satellite problem. We will also take a look at the predictions for the Lyman alpha forest that involves considering the absorption lines of neutral hydrogen at high redshift, which is widely considered to be a rather accurate probe for small-scale structure. Now, instead of a full hydrodynamical simulation that involves dark matter and neutral hydrogen, which would be needed to obtain predictions for this observable, we will instead choose to use a rather more simple approach as outlined by this paper right here by Murgia and others in 2017, which would simply measure the deviation of a power spectrum from a Lambda CDM reference. And we can see the results of this analysis here on these plots for self-interactions mediated by a vector field acting on non-SMCR neutrinos with low active sterile mixing. In the upper panel, we can see the number of Milky Way satellites as a function of the particle mass and the interaction constant. We can see that if we stay in a vertical line in a given mass for low interaction models, for lightly interacting models, we can see that once the interaction constant becomes high enough, these particular mass models become, well, you can see a definite transition there on the non-relativistic self-decoupling transition, and you can see that the model becomes colder and the predicted amount of structure grows significantly. Well, on this plot, we put a few constraints. For example, a lower limit on Milky Way subhalos estimated to be around 57 based on the observed amount of subhalos, of course. and an upper limit on the self-interaction constant based on observations of the bullet cluster. So in the lower panel, you can see the Lyman alpha, the non-cold dark matter deviation magnitude relating to Lyman alpha observables. We consider in this analysis a model as ruled out if it shows a higher deviation than the reference 3.5 keV mass thermal warm dark matter model. As shown to be the limiting case in this paper right here, it's shown that a thermal warm dark matter model with masses lower than this is excluded. So we consider the model to be excluded if it's more deviated from Lambda CDM than this reference model. Well, we can see particularly here that Lyman alpha observations can exclude a large amount of the parameter space for lightly interacting models, but once we move to the regime of strongly interacting models with a non-relativistic self-decoupling regime, these models become reallowed. We can see this particularly more clearly in the plot for the parameter space bounds of this sternocleido warm dark matter model we considered. We can see here the exclusion lines from this work of Lyman alpha from BL in 2013. Here we can see this dotted gray line here, and due to Lyman alpha observations, all of these models to the left of this line would be completely excluded. Now, this is in the non-interacting case. Now, if we move to the highly interacting case, this line here moves to the green line here. We can see that a lot of these dark matter models, these self-interacting warm dark matter models, become reallowed, readmitted thanks to the effects of self-interactions as the models become colder, without needing to alter the particular particle mass of the dark matter model. So we are actually reaching the final part of this seminar, and here I would just like to propose a few future prospects and future directions of research regarding these models. Here I will mostly present self-interacting warm dark matter probes among several observables. For example, we have the 21 centimeter observation data, this potentially upcoming observation of the 21 centimeter hydrogen line. These emissions give information about structure at the very early stage of the universe, potentially on redshifts between 10 and 30. These sort of observations could probe linear structure up to very small scales. It would be sensitive on the power spectra up to scales of 300 inverse megaparsecs or lower. This can not only probe the suppression of the power spectrum. We've seen before that typical warm dark matter suppressions are in the range of tens of inverse megaparsecs. So this could not only probe the suppression, but also it could probe the oscillations in the power spectrum. These oscillations are obviously characteristic of self-interacting warm dark matter models, but also of other types of interacting dark matter models. So for the case of self-interacting warm dark matter, it can be an interesting probe, but it is rather challenging on the numerical aspect. It requires high definition simulated data for high wave number modes. These small scale computations take a rather long compute time because it is needed to integrate a rather large system without any significant approximations for most of the evolution of this mode. We can see this, for example, in the tight coupling approximation, the most relevant approximation in this system. Here we can see the regions of validity of this approach as a function of wave number and redshift. And we can see that for increasing wave number, the region of validity of this approximation becomes smaller and smaller, and the wave number spends integrating a larger and larger amount of time without any approximation. So it would be important to find an approximation scheme relevant to this late time high wave number, small scale regime for self-interacting modern matter, and this remains an open question subject of current research. Another very interesting future prospect would be of for self-interacting modern matter probe would be in stellar streams. These are torn and stretched structures formed by tidal disruption of clusters. The perturbations on these structures show memory of gravitational perturbations by passing structures. So in short, light or dark scatterers would pass through these structures and leave small gaps in them. The statistics of these gaps would be sensitive not only to the population of small structure in the universe, but also to its shape and its mass. This can provide an interesting observable, not only for the free streaming scale of dark matter, but also the concentration of scatterers, which would indeed provide an interesting observable for these rare systems. So now we have reached the end of this seminar. I will present here a few concluding remarks. We presented these halos from maximum entropy production. We discussed a few of these observables and its stability. We motivated here this approach of self-interacting modern matter models and revised some early model constraints from helomorphology. Then we developed a full theoretical framework for dealing with these models in a more cosmological setting. We performed a numerical application, we presented a public Boltzmann code, and we compared the results of this code with astrophysical observables. And to give a summary of interesting future prospects and research direction, apart from the observational probes I already mentioned in the 21 centimeter and stellar stream observations, we could have further substructure observations that would give us hints to the process of structure formation and population of this small structure in the universe. Also, from a more theoretical point, we could provide further research into self-interacting quantum matter particle production and perform a deeper analysis into the assembly history also related to the process of formation of these rare systems in the first place. And on the more numerical side, we could propose a full application of these integration kernels and provide better approximation schemes for these Boltzmann solvers. Well, thank you very much for listening, and I remain here open to any questions that you may have.
Thank you so much, Rafael, for the interesting talk. Very nice stuff. A lot of stuff, by the way, but very, very nicely condensed in 40 minutes. So thank you so much. Okay, so are there questions or comments for the speaker?
Oh, first of all, I would like to leave the link to the GitHub page if you are interested. Stop sharing the screen for a second, and let me see if I can.
Yeah, you can put it on the chat
here. Yes, of course. Here it is. There we go. Thank you.
Okay, so time for questions or comments. Okay, so I may have a few indeed, although you and me already chatted a bit about all this stuff. Let me maybe focus on some new stuff. You were mentioning the use of stellar streams as a proof of these kind of models, right? So
exactly.
Yes. So something I don't totally understand, because I think with your power spectrum, you actually erase superstructures below, I don't know, 10 to the 7, 10 to the 8, 10 to the 8.
Yes. I mentioned 10 to the 5, 10 to the 5, 10 to the 6, and lower. It depends on the. It depends obviously explicitly on the dark matter particle mass.
Okay.
I mentioned that a few slides ago. So yeah. Like I know that these observables would actually be sensitive to this cutoff scale. How small can these scatterers be, or what are their population, obviously?
Yes, because my concern was actually that with this kind of methods, gaps in stellar streams, you can actually, I mean, people already are measuring or weighting subhalo masses of order of 1 million solar masses or so, right? So if that's correct, well, perhaps you could already use this as a kind of limit for your models as well, right?
Exactly. That's what we're mentioning here, that this can provide some interesting constraints. Like all of these observations can provide some really interesting constraints to limit the scatterer mass, or observing already scatterers at a certain mass, or a significant population of scatterers at a certain mass can already give you a very clear limit, for example, of the dark matter mass particle, or the combination of the particle mass and the interaction strength, obviously, because you have seen that the process of structure formation depends both on the dark matter particle mass and the interaction constant. So yes, it's very interesting for actually putting a constraint on these models themselves, and also even possibly on the shape of the scatterers.
But do you think that you can actually differentiate somehow these models, between these models and the classical warm dark matter models? I mean, given the way the power spectrum behaves in both cases, do you think you can actually differentiate between both the scenarios?
With this, I am not exactly sure. Now, obviously, depends on the particle physics counterparts of warm dark matter. One, just to not stay with this stereo-neutrino model, one typically expresses these things in terms of equivalent thermal warm dark matter particles. It's a model that's not really excluded, but it would require particle production in the extremely early inflationary universe. So people are not considering it so seriously. So yeah, like one can in principle say, well, this population could put you a limit on the smallest amount of structure available, let's say. If your observable can only limit the free streaming particle mass, it would just say any dark matter model that has a power spectrum suppression and is more or less or more suppressed than this would be excluded, and it would give you an interesting obviously constraint, but obviously it wouldn't be let you be able to differentiate between one model and the other. Now, if you have an observation so precise that it can give you exactly the shape of the power spectrum that it would make it, of course you could differentiate between one model or the other.
Yes. Okay. Good. So let's see if we have questions from the audience. Does anybody has a question or comment for Rafa? If not, I actually have one more about this thing about the profile.
Please don't be shy.
Yes. So I have one question about the density profiles. Perhaps you can actually show what you got for the Milky Way, where you show this comparison between your profile and the data itself for the Milky Way.
Oh, this is the rotation curve, not the density profile.
Exactly. So I was wondering if you wanted to use this same, because this profile actually means that you are assuming a particular set of parameters for your model, right? I guess, right? So in order to explain all these observations, you use a set of parameters so that you can actually end up with this profile that nicely reproduces the data. So I was wondering what happens, or if you checked what happens if I go now with this same set of parameters to other targets, other astrophysical objects. No, if instead of using Milky Way, I now assume that this set of parameters is actually the right one, and then I go and check in other astrophysical targets. Is that compatible? Did you already do that?
Of course. I mean, actually, you can ask Professor Arguelles, that I think is right here. By minimally altering these parameters, you can describe many other objects, astrophysical objects. Well, mostly dark matter halos, for example, dwarf galaxies or ellipticals or others. Actually, he is leading a project right now by fitting a lot of a whole catalog of galaxies, of spark galaxies with these models. Obviously, you need to change the parameters slightly, not the particle mass, but temperature, the thermodynamical parameters between the solutions to give you other morphologies of solutions, some that would resemble more dwarf galaxies, some that would resemble more ellipticals, but they are actually doing a comparison of this model, the fits for this model, with a bunch of other galaxies, and comparing that with standard models for fitting these astrophysical objects. I think Carlos wanted to talk.
Hello, everyone.
Hi, Carlos.
Yes. Hi, how are you? Can I make a comment on this? Because yes,
of course, go ahead.
Good. So yes, this is a good question, because when we first published this work about Milky Way, it was of course the best case we have, because we have the best resolution towards the center in order to test these dark matter concentrations. We then moved to dwarf, typical spirals and ellipticals from different data sets. And indeed, for fixed particle mass, let's say 50 keV, which is a typical mass in this analysis, we have a model of 3 free parameters: the temperature, the effective temperature of the dark matter, the degeneracy, which is how much concentrated towards the center is this dark matter, and the cutoff parameter or escape velocity, let's say, of the dark matter particles. So there's with these three parameters, you can have a lot of flexibility to fit the dispersion velocity in dwarfs, and also rotation curves in other disk galaxies. And yes, so we have also the windows of all these free parameters that agree with all of these observables. One last comment is that interestingly, we are now comparing, for example, with the state-of-the-art dark matter models, for example, generalized NFW, which accounts for, baryonic feedback, or also isotope profiles, which are, high-resolution dark matter-only simulations, and which are the best, let's say, that reproduce overall, for example, from the Spitzer catalog of galaxies. And we are now making the statistics and achieving a very similar minimum in reduced chi-square respect to those models, with meaning to be comparable, statistically speaking. So this will present in short these results, which is interesting because it is giving you or the community another paradigm of putting into the game a known old paradigm of formation, of course, which is maximum entropy production, which is an alternative because the dark matter particles will reach quasi thermodynamic equilibrium, differently from standard CDM only simulations.
Yeah, thank you, Carlos. Yeah, very nice.
Thank you.
Stuff, as I said. Okay, great. Are there more questions or comments apart from?
I hope
from my comments and questions. We still have some time if needed. Don't be shy. Okay. So in any case, just feel free to contact me in case you want to contact Rafael, or just Google his name if you have any further comments. Yes, exactly. Okay, so I think we can then, if there are no more questions, we can maybe close here.
Well, thank you for having me, and
thank you so much, Rafa, for this nice talk, and good luck. Okay.
Thank you.
See you around, guys.
And see you.
Have a nice evening. Bye bye.
Goodbye. Thank you.